Hi, this is Steve Gibbs again. This time we're going to look at part 2 of solving linear equations, and this time we're going to look at how to solve linear equations using matrices. So let's go back and start solving our linear equation, this time using matrix algebra, based on the problem we started with to begin. Let's find the price of apples and oranges. When 3 apples plus 5 oranges costs 1.70, 5 apples plus 1 orange costs 1.00. So how much does each apple cost? How much does each orange cost? We mentioned at the beginning that we were going to use 4 techniques for solving linear equations. We've already looked at substitution. We've also looked at the graphical solution process. This time we're going to look at solving equations with matrix algebra, and then the next video segment we'll look at Cramer's rule. So let's go back to our original equation. 3 apples plus 5 oranges costs 1.70. 5 apples plus 1 orange costs 1.00. And let's put it into matrix form. Okay, complicated. So let's step back and let's look at how we're going to work with a matrix structure to solve the problem. As we look to start solving linear equations using matrix algebra, there is a format that we use to define the matrix. We start with the matrix A times our unknowns equals our result matrix, or our result vector. The matrix A is a 2 by 2 matrix. Notice the positions A, B, C, D, and putting our original problem into it, we have 3 apples, 5 oranges for the first part, and then 5 apples and 1 orange for the second part. So that's how we load data into our 2 by 2 matrix. X is our 2 by 1 column vector, and it contains the unknowns. B is a 2 by 1 matrix, but in this case we put our coefficients in it, the 1.70 and the 1.00, that represent what we know to be our output costs. In order to solve our linear equations, we'll start with our basic format. The matrix A times the unknowns equals B. The solution is calculated using our unknowns is equal to the inverse of A times B. Now it looks algebraically like we could rearrange this to say that X is equal to B divided by A. But we're not allowed to do that when we're working with matrix algebra. We have to calculate the inverse of the matrix. So how do we calculate that? Well, the formulation for it is that the inverse of A is equal to 1 divided by delta, and delta here stands for the word determinant. We'll look at calculating the determinant momentarily, times a new matrix, which is a transpose of our original matrix, where now A is in the bottom right, B is negated, negative B, minus C, and D. So instead of A, B, C, D, we've got A minus B minus C, D. So now, how do we calculate the determinant? This is another format. Notice instead of square brackets with matrix terms inside it, now we're using straight lines. And that is, in definition, the determinant of matrix A. Well, the determinant is equal symbolically to taking the A out and again putting the terms in that make up A. And it's calculated by saying AD minus BC. So in our case, If A is equal to 3551 as a matrix, then delta is equal to 3 times 1 minus 5 times 5, which is going to give us a minus 22. Okay, so let's take what we've seen about structure and put our pieces in place. If we know that the inverse of A is equal to 1 over the determinant times D minus B minus C A matrix structure, then by plugging our numbers in, the inverse of A is equal to 1 over minus 22 times our matrix, which is 1 minus 5 minus 5, 3. Well, since we can take and multiply into the matrix directly, we simply take that 1 over minus 22 and multiply each term by that value. So now we have 1 over minus 22, minus 5 over minus 22, minus 5 over minus 22, and 3 over minus 22. Well, now we're starting to get to the solution. If x, our unknowns, are equal to inverse of A times B, now we have x1, x2 is equal to our inverse of A times our result matrix, which is the column vector 1.7, 1.0. And now we get to calculate that. If we start with this structure, we find out that we can take this 1.7 and multiply it by the terms in the first column. 1.0 gets multiplied by the terms in the second column. Now this is a little bit complicated, worth paying some attention to come back and look at, remember how it's done. But once we've done that, now we can see with this structure, just multiply the terms out, that x1 is equal to, or x1, x2 is equal to this matrix structure. But here's the last piece in the matrix, in the analysis. x1 is going to be equal to minus 0.07727 plus 0.22727, and x2 is going to be equal to 0.38636 minus 0.13636, taking the signs into account. But what that leads to is that x1 is going to be equal to 0.15 and x2 is equal to 0.25, which is the solution to our problem. So starting from this, there's our calculated answer. So in a different format, we can say that x1, x2 is equal to 0.15 and 0.25. Going back to our original problem, 3 apples plus 5 oranges cost $1.70 or 1.70. 5 apples plus 1 orange costs 1.00. Learning that x1, x2 equals 0.15, 0.25, that tells us that apples cost 0.15 or 15 cents each. Oranges cost 0.25 or 25 cents each. So we've looked at 4 techniques so far. We've already dealt with substitution. We've already dealt with graphical. This time we looked at matrix algebra. Now the matrix algebra gets pretty complex, especially if we go larger than a 2 by 2 matrix. But this is a start. You can go back over and review it. Next we're going to take a look at Cramer's rule. Hope you're having fun with this. Come on back for the next lecture and we'll look at Cramer's rule.